Welcome to the Data and Decision Making for Operations webinar. Hello, everyone. My name is Luana Brashears. I will help facilitating today's webinar. This webinar is hosted by the National Operations Center of Excellence. And today's webinar will include two presentations: a framework methodology to support data fusion analysis and decision making, and data integration, sharing, and management for transportation planning and traffic operations. So just as a quick reminder, if you don't know already, at NOCO, we offer a variety of resources to support the transportation systems management and operations community. You can go to NOCO's website to browse through links for TISMO resources and news. Previous webinar recordings and case studies can be accessed from here. A few logistics for our meeting today. We're recording this webinar, and the recording will be available on the NOCO's website later. All the attendees are encouraged to stay engaged by using the Q&A and chat pods for comments. So those will be in the bottom of your screen. And if you have questions, we'll have question and answer sessions at the end of each presentation today. So at the end of the first presentation, we'll have a quick Q&A session. And then at the end of the second presentation, we'll have another Q&A session. So our first presenters today are Nikola Ivanov and Sean Chen. And the first presentation will be a framework methodology to support data fusion, analysis, and decision making. Nikola serves as the Director of Operations at the Center for Advanced Transportation Technology Laboratory, the CAT Lab, where he manages operations and technical development and oversees every aspect of software implementation from conception to deployment. Nikola has extensive experience with big data and information visualization, focusing on translation of data into actionable information. Sean is a full professor jointly appointed at the Department of Civil and Environmental Engineering and Heinz College of Information System and Public Policy at Carnegie Mellon University. He directs the Mobility Data Analytics Center, MAC, at CMU. Chen's research interest lies in large-scale dynamic network modeling and large-scale data analytics for multimodal transportation systems and development of intelligent transportation systems, ITS. As a reminder, please add your questions to the Q&A pod. Nikola and Sean will address them following their presentation. So now, Nikola, if you'd like to share your screen, please feel free and start whenever you're ready.
Sure, thank you, Luana. Okay, you should be able to see my screen now. All right, great. So thank you for having us here today to talk about a framework to support data fusion analysis and decision-making project. Sean and I worked with a few other folks on this project for the Federal Highway Administration. And today we'll walk through that research and the outcomes of that research. So first, just a brief disclaimer that this is a presentation that we've created as contractors for the project, and it doesn't necessarily express the views of the FHWA and so on. So this is a necessary disclaimer that we need to include here. So in terms of introduction for this project, the goal of the data fusion framework was really to support decision making by reducing human error, institutionalizing data fusion processes to improve that decision transparency, and then really to maintain the stability when it comes to data-driven decision-making. And that stability comes from retaining that institutional knowledge, improving that transparency, reusing data projects and so on. So again, the idea here was to establish a framework that would allow for all of these benefits to manifest themselves with any agency that implements this framework. So in terms of the impact of this framework, the key impacts include tying the lower level operations decisions and actions with the upper level goals and objectives. So again, it's kind of crossing different boundaries within an agency at different level, and then providing these connections allows the framework to enable agency managers to visualize these impacts and adjust their decisions based on new insights from data fusion processes. So again, taking different data sets, performing the analysis and the fusion of these data sets, and then using the outcomes of those analyses across different levels of the agency to inform their decisions, both from an operational, tactical standpoint, as well as more strategic operations standpoint. So in terms of the target audience for this particular framework, it supports many different groups within a DOT, as well as the outside stakeholders, information technology staff, partnering organizations, and so on. It's applicable across multiple levels of the organization, as I mentioned, from TMC operators, emergency management, et cetera, to executive management. But then it's also bridging the gap between operations and IT and system integrators and developers as they develop the systems to support operations using data and data fusion. So again, the goal is to bridge those gaps and allow agencies to capitalize on their data investments on all different levels of the organization. So briefly, on a high level overview of this framework, it consists of 5 major sequential steps. Each step has multiple sub-steps in it. And in the report that we built for this framework, or in the framework, you can actually go between different steps and sub-steps and orient yourself in terms of where you are in the framework and where you need to go in the next step of the framework. Now, these steps are sequential, but at the same time, not all of the sub-steps will always be relevant. And so different use cases capitalize on different areas of this framework. And therefore that framework is flexible enough to support multiple use cases and scenarios. And then it also has a feedback loop, as you see from the evaluation step back to analysis step, to evaluate those results and improve the future decisions. So on a high level, it's a 5-step framework with more detailed sub-steps within that framework. Now, briefly to talk about the difference between analysis tools and methods, we want to clarify the relationship between these two things because it might be of relevance to implementation of the framework. There are tools out there that help prepare, clean, analyze, and report data, but it is useful to understand the underlying methods that the tool may be executing to achieve those goals. So in this example, we're thinking of the tool as a car that is powered by those methods, which is the engine of it. So again, the tools and the methods are delineated in this framework so that we understand the underlying work that needs to be done to make those tools effective and the outcomes useful. All right, so moving into the actual framework here, I'll walk through a few steps of the framework before I turn it over to Sean. The first step of the framework is to ingest data. So what we've done is we define 7 different categories of data, and you can see them listed here. These are fairly broad categories that consist of many different types of event and incident data and traffic performance data and so on. And what we've found in the framework is that the single category fusion is useful if you want to improve quality of information. So fusing data within a single category might be taking the same type of data from multiple sources, or maybe with different properties, and then putting it together and determining, exposing maybe the more accurate data by looking at multiple data sources and so on. However, if we look at multi-category fusion, that can actually bring additional insights and benefits because we're combining data and information from different sources as well as of different types to get a more comprehensive picture of what's happening out there. And so there are different types of benefits of combining these data sets, as well as some of the drawbacks of treating data as information. Those are 2 separate things. And so we in the framework, we talk about how as you ingest this data, you have to think about these different data types and how they would fit into different categories and implications for the fusion. I went the wrong way here. Traditional data and information tends to be well-defined and structured. This is as we were starting to collect more data out on the roadways. A lot of it came from sensors that were specifically calibrated and provided only certain small sets of data. And so in the past, we were able to manage that data using traditional relational databases and extract and transform and load processes. Just because this is a traditional approach doesn't mean that it's not important and relevant. It's still important and relevant. But as we are getting more data from more different sources, it is important to understand that the big data that's out there today may involve different approaches to it and involve things like sampling and streaming, also using the non-structured data storage and processing systems, because the data might not be well structured. For example, if you get something that's coming from a crowdsourced data source, then it may have a different form and not be able to be fit into a standard relational concepts. One of the key things in this first step of ingesting data that the framework advocates is storing data at the lowest possible granularity. This is important because if data is overly granular, you can always roll it up or aggregate it to a level that's needed for a particular application. However, it's a lot more difficult to go the other way around. If data is not very granular, trying to expose some of the more nuanced information out of that data may be difficult or impossible in some cases. So the goal is to ingest data at the lowest possible granularity to support different use cases. In the second step of the framework, we take data that we've ingested and we start the process of cleaning that data. And cleaning that data includes assessing the quality, tagging it and cleaning it, and then doing some initial fusion. So on this slide, you're seeing a number of different data cleaning checks and actions that are taken. So for example, presence. Are there entire expected records that are missing out of the data set, and how do we handle that? Completeness, are there some elements within that data record that are not available? In terms of uniqueness, this is especially the case if we're looking at multiple sources. We may be getting the exact same data, and so this data may already be present in our system from somewhere else. From a consistency standpoint, it's just looking at this data and saying whether or not it makes sense. So maybe it goes through all of the error checks and the numbers are all good, but do they really make sense? That's the consistency piece. Range constraints, so that's more of a standard checking of the boundaries for a particular value. Error checking, standard validation. So if somebody's claiming that the data is in a particular standard, is it really validating to that standard? And so on and so forth. So these are all the different steps that you can take within the cleaning step once you ingest the data to utilize it. And then as you do that cleaning, you move to that fusion piece, and the true value of this data really is exposed once you start fusing it, either with similar data sets or disparate data sets. So the goal of the fusion is to improve the quality of the data set and or to extract new information that may not be available from a single data source. And there are several elementary data fusion types. For example, there's spatial fusion, which is where we match things based on their spatial extent. So maybe it's looking at event data matched with TMC code, the traffic message channel code, a link on the road, for example. Temporal, again, looking at data that's temporally close to each other. So maybe it's a sensor data set with an event data set or with some other data set around the same time and spatially around the same location. Complementary, redundant, and cooperative are three other types of data fusion, elementary data fusion that allow these different data sets to either complement each other or maybe validate a particular, in terms of redundant, validate that the speed coming, for example, from probe data is matching the speed coming from a loop detector. And so it's validating the ground truth. And similarly, cooperative, where we're looking at two different data sets indicating maybe the same type of an event happening out there. So in this case, weather data, looking at that versus connected vehicle traction control activation and saying, yes, we know that there's ice here, and traction control data is showing us that it's being activated in this location. Therefore, these are kind of a cooperative data fusion approaches. All right, so step 3, I will turn it over to Sean.
Thank you, Nicola. Good afternoon. Nicola already described at the very high level how we can process the data, fuse the data. So now imagine that you have all the data all lined up, right? They all add up in the same row segment with all different type of incidents, speed, counts, whichever data you choose to use. It's all lined up right now. But the ultimate goal for any so the applications of these data fusion techniques is really to go to decision making, right? We want to get as much of insights as we can, and also make any sort of decision making, make the best use of the data. So next few step is really a few steps about analyze, about decision making, about reevaluation, feedbacks. So these are step 3, 4, 5 that I'm going to talk very briefly at the very high level. Then I will go back to give a couple examples and one particular case study. Then I will hand back to Nicholas to present another study and for this for the whole research report. About analysis, this is step number 3. Once the data is all fused geographically or temporally, then we want to apply some sort of methods either to visualize, to extract some insights, not necessary to make any decision yet, but this is the step for us to get some understanding of the system dynamics. For example, if we know the current speed is 25 miles per hour, maybe you want to analyze the data to see, hey, historically, is this really above average? Is it below average? Not necessarily making a decision yet, but this is a very essential step that we are going to apply some of the statistical models or AI machine learning models of our choice. It can be very, very simple, as simple as, hey, we can set up a rule, expert rule, anything beyond 25 miles per hour will be anomaly, right? As simple as a rule. Could be also as complicated as we apply very sophisticated machine learning algorithms, supervised learning, for example, just to use 10 years of data, learn everything whether we just fused from history and then to set up certain rules that comes from machine. So anyway, this my point being, this is really applications or analysis that we try to understand the system better before we even make any decisions. Nicholas, next page. Right, here's another example. This is the example for the unsupervised learning, namely clustering. Imagine that we have all the data, row segments, time of day, season, weather conditions, incidents, work zones. And then this is just an example showing if we fuse all the data together in the same geographic zone, maybe in a year or maybe depending on, again, the temporal scope of your choice, we can do some clustering analysis, really saying, hey, this is a typical winter Wednesday sunny day, or this could be a typical atypical summer humid day with a crash on highway X, Y, and Z. So once we cluster, this is what we call typical pattern. Once we have it, and then we can develop, right? We know this is a typical pattern, and we can develop a specific response plan. Namely, the next step is really the decision making for each specific pattern. Next page. And I want to talk a little bit about the AI machine learning, and then this is kind of very can go really, really sophisticated, but oftentimes the machine learning part is really applies to analysis. It's really about, it's part of AI, but it's not entirely AI. Machine learning means that we want to apply statistical models and machine learning algorithms to understand the system dynamics. Like I said, we only wanted to understand the system, but before we make any decisions. Nicola, next page. Yes, and AI is really about the whole process, starting from the fusion all the way to the end of making any recommendations about decision making. This is the whole process. We try to automate the process. Of course, machine learning is being part of it, right? Next step. Right, so this is again a graph about depending on what type of problem you're addressing, depending on what kind of data available to you, depending on your comfortable zone about how sophisticated model you want to be. And then depending on many different criteria as we listed here, the problem solving can, and then the kind of data you use can go from very simple to medium to very, very powerful tools. And then that really also corresponds to, is this really a quick and kind of dirty kind of planning, or this is really, you want to go as much granularity as you can about the micro simulation or micro level management. And then accordingly, you're going to use different data fusion methods as well analysis of decision-making methods. Next page. And the step 4 is about decision. Once we learned about system, for example, we predict the system is likely to going to have anomaly in the next 25 minutes. And we know the system, now it's time for us to make a decision. So this decision, there are many different types of decisions we can make strategically, tactically, and operationally. And there are also different methods that we can use. Ideally, we want to, that's what by the name of AI is, that we want to automate everything, right? And then without really having any human to intervene the system, which is oftentimes what we think is not so ideal, because we really want to have a lot of expertise from the professionals who can see the real system conditions and to intervene the system at the time we need. But having some sort of intelligence from the machine that we can learn from the past and automating the process in the way that keep human in the loop, and then making sure the system doesn't go wrong is really what we recommend. But we do have different levels of engagement of the data fusion and then decision-making process. Automated, operator, entirely human, and human in the loop are 3 different things. Next page. Okay, so the step 5 is about assessment. It's really, really important that everything we just talk about is analysis and decision making. We start from somewhere. We have to start from somewhere, and not necessarily learning about the optimum of the system. And then we do, because we have the data. Again, this is also being part of the data fusion. Is that after we engage the system, after we're making some kind of decision, and post the decision, it's really crucial for us to collect the data again, the same data you just fused to make any decision, just to see, hey, well, does it really meet my expectations, and how does that thing, the KPI changes over time? Are we really making the good decisions? If it's a bad decision, can we go back to the step 1, 2, 3 to engage different sets of data, or maybe we find there are biases in the data, we want to go back and change it and correct it. So this is another step that we are talking about, that essentially we need to have some kind of feedback loop to improve the whole process over time. Next page. So this is really about just line up with the step 3, 4, 5. This is about analytics part of it. Again, I try to emphasize we can look at this whole process at the strategic level, tactical level, where you go change the program, change the investment, capital investment, but can also get at the very operational level. You can tune the signal timing, give feedback, and to improve the system, change different clusters, and develop a different response plan for each class, and etc. Next page. So I'm going to very quickly present 2 case studies. One is a data fusion and decision-making case study we applied to Cranberry Township, a traffic management center. And then Nicola will talk about another case study implemented in PennDOT. Next page. And this is a very kind of a real world operation. And the idea is very simple. Now all the traffic management centers, I'll give you a little bit of background. Cranberry is a town roughly about 25 by 25 mile area. But what's so unique about this township traffic management center, what's so challenging, is because it sits in the intersection of 1 turnpike, 1 highway, interstate, and then 2 state route. Very busy traffic, and anything go wrong, that's what they call doomsday, right? So if something goes wrong, any of the 4 highway segments, and then the whole township and will get into the gridlock. But now the reality is that they have a lot of data, cameras, index data, speed counts, incidents report, 911, 311, everything. But the data could be very, very overwhelming. How can we translate the data to some sort of decision making as early as we can? Because in these traffic management center, I think the timeliness and then being proactive rather than reactive is always the key. You want to get ahead of the time when you see there's a congestion. So the goal here is trying to, hey, look, we have all this data. Can we fuse them and then analyze them and then make proactive and ahead of the curve decisions as early as we can? Next page. And then that decision will send automatically, right, 24/7 to the traffic management center staff. And what we do is the details in the report, but I think the very high level, we fuse the weather, incidents, crowdsource data, with Waze, and social media, travel speed, PennDOT incidents data, state data, and then we use the machine learning model to train it about 2 years of data, and then make the predictions, set up certain rules, and alert the traffic management center 24/7 about, hey, something's going to happen in next 30 minutes. Maybe it's time for you to start to engage signal timing and contingency plan X, Y, and Z. And then we also tell them when to stop, and then if we anticipate the queue will dissipate very quickly. Next page. So some of the very brief performance metrics, we talk about the evaluation. We do in the past 2 years, 3 years actually, the system has been deployed in the TMC, and we do see that traffic congestion under incidents has been reduced quite substantially. We also see that, and oftentimes the system with the data fusion, because the data give us a lot of information about predicting when this anomaly is going to happen, and then we're able to get ahead of the curve roughly about 15 to 25 minutes earlier than a Waze report. And everything is automatic and then 24/7, and that's only a message away. Next page. Okay, Nick, I hand over back to you.
All right, thank you, Sean. So I will briefly talk about the PennDOT use case that Sean mentioned earlier. So in this use case, PennDOT has developed a congestion causes dashboard. The idea behind this dashboard was to fuse multiple data sources and create a dashboard that would be informing the operations at different levels of the organization. And so what they've done, similar to what Sean described with the Cranberry Township, weather data from different weather stations and traffic applications, as well as data related to speed and congestion. This was coming from the private sector data provider, and then event data from multiple sources. So they had data coming from traffic applications, police records, probe data, and their own incident data. So they were fusing these 4 categories or 4 types of data, but within those sets, there were multiple sets as well. And they were using some of those elementary data fusion methods that I mentioned earlier in terms of temporal, spatial, redundant data fusion. And so what they've done is they've developed a dashboard, and this is an example of that dashboard on the right side of the screen, that allowed them to expose a lot of different insights. So first, they were able to identify when and where the congestion was occurring. They were able to do this in real time, and they were able to look back at different time periods as well. And then they were also able to assign confidence scoring for different data sources. So as I mentioned, not only were they utilizing multiple data sources, they were able to provide more information about which data source may be reliable in which particular case. It's not that one data source is always more reliable. It could be that different use cases warrant different type of weighting. And then they were also looking at congestion causes for those events. So whether they were happening because of weather or it's a particular event occurring, or if it was a recurring congestion type of a thing. And then they were also looking at all of this in near real time in terms of regular schedule, where they were able to update this congestion, this causes of congestion dashboard, and then also use the information that they've collected and fused together to plan for some of the bigger events. So in terms of the utilization of this dashboard, as I mentioned, planners used it to justify some of the investment decisions. So they were able to look at things like user delay cost as it pertains to different sources of those delays. So in this case, you can see graphics here for 12% of the user delay costs are due to incidents versus 2% for work zones and so on. Now, they are not using this in real time necessarily. As I mentioned, it's kind of a regular near real time dashboard updates. But the goal here is to start adding additional data sets to boost the information in the, or allow decision makers to have more information to work with. So for example, using trajectory data for signalized corridor analysis and things like that. In this case, you can see that user delay cost is 17% in this particular case was caused by signals. So understanding a lot more about how signals are contributing to those user delay costs are the goals for this dashboard. What was great about this is that the success of PennDOT use case has been inspiration for other agencies outside of PennDOT to start to create similar tools and utilize them for their operations decision making. So that's the PennDOT use case that covers the brief summary of the framework and the project. The report is available out there. We can take questions now. I don't see any open questions in the chat, but I will also put James. I know he's in the call as well. This is his contact information if you have any questions after this meeting as well.
Thank you so much, Nicola and Sean. Very informative presentation. We do have one question in the pod. It asks, can you put the link to the report in the chat pod when you have a chance, please? And then this is the only question I see for now. So this is what we'll do. We'll go ahead and get Kelly to start her presentation. And then we will just address all the questions in the end. So you have two options. You can either type your question to the chat pod, or you can raise your hand at the end of Kelly's presentation, and then I can allow you to talk and you can ask your question if you'd rather do that than just typing it in the chat pod. All right, so thank you so much again, Nicola and Sean. That was a very informative presentation. And now we'll move to our second presentation today. Data integration, sharing, and management for transportation planning and traffic operations. And this will be conducted by Kelly Picha. Kelly holds a PhD in civil and transportation engineering from Penn State University. She's the Senior Director of Transportation at AEM Corporation and the Principal Investigator for NCHRP 8119, Data Integration, Sharing, and Management for Transportation Planning and Traffic Operations. As a reminder, one more time, please add your Q&A, your questions to the Q&A chat, or you can just ask them in the end. And with that, I will stop sharing my screen. And Kelly, whenever you're ready, you can start your presentation.
Okay, can you see Luana, the screen?
Yes,
okay.
I can see it.
All right, okay. Good afternoon, everyone. I'm going to be talking about NCHRP Project 08119, Data Integration, Sharing, and Management for Transportation Planning and Traffic Operations. So just a quick overview of my presentation. I'm going to give a little bit of information on the project, talk about the research approach, the research products that are currently under development, and a timeline for product availability. So NCHRP 08119 began almost 3 years ago, September 2019. It's still ongoing. The objective of the project is to develop tools, methods, and guidance for improving data integration, sharing, and management practices to enable transportation agencies in collaboration with private sector and public sector stakeholders to make better planning and operations decisions. I have a great team working on this project. It's AEM Corporation, Jacobs, McGurran Consulting, and Pat Noyes and Associates. And we are hoping to wrap up all of the draft products by the end of this year, and hoping that the project will probably be over. We are currently working on extending it a bit, but looking to have it fully wrapped up by the second quarter of 2023. So the research approach involved 5 phases that were in the work plan. The information gathering and planning, which was about the first year or so of the project, was really doing a broad sweep across a wide range of operations and planning use cases. And so things like, work zones, freight, connected automated vehicles, shared mobility, ICM, et cetera, and conducting a lot of interviews and doing research and trying to identify where there were challenges, gaps, or limitations within these use case areas for data sharing, integration, and management. So where agencies were working to share data or integrate data or manage data, where were there challenges that could possibly be addressed with this research project. Phase 2 was documentation of best practices, lessons learned, and also, again, challenges and limitations. So this phase is also complete, and it resulted in a website, which I'll talk about in a minute, because it's one of the products or outputs of the research. Phase 3 was to develop products. So at the end of phase 1, the research team, we put together, I think it was over 30 potential products. And again, those products could be tools, methods, guidance that would be available for agencies to help improve data sharing, integration, and management. So we went through all of the challenges and limitations across all of the planning and operations use cases, and we recommended or developed potential products that could be developed as part of this research for the panel. And the panel reviewed those and kind of weighted and rated, and we narrowed it down initially to 8 products out of 30 some that we would focus on. And those products have been modified a little bit as we've continued the research, and some have been replaced or added. And that's really the primary focus of my presentation, is to go over those products that are currently being developed. Phases 4 and 5 are really kind of sequentially happen as we develop the products. We're trying to work whenever possible with agencies and organizations and stakeholders for these products, and work to get their inputs into the product, and then ask them to review the products and provide feedback so that they will be applicable and useful to the industry. So this is the list of 11 products that were either have completed or are currently working on. And I won't read this list because I have a slide on each one. But it differs a little bit from many NCHRPs that might result in a final guidebook or a final research report, or maybe both. In this case, we're really focusing on developing these products for these specific use cases. And there won't be a final guidebook or a final research report. Rather, we've got these 11 different products that we're working to develop as outputs for the research. So just starting to go down the list of the products that we're working on, I mentioned that the outputs of phase 2 were documentation of lessons learned and best practices. And we have done that in the form of a web-based research library. So we have a draft version of the website that still needs to go through TRB publications review. It presents the relevant knowledge, use cases, data sets, metadata, tools, et cetera, that were identified in that first phase of the research. You will also have all of the research products will be available on the website here. They'll also be available on TRB's website, but can access them through this website as well as additional resources that have been uncovered throughout we did a lot of research in phase 1, but then we've also done additional research in the development of the individual products. And so where we've identified additional resources that might not fit within the structure that we developed at the end of phase 1, we've added additional resources. And these are sort of cross-referenced across these areas. The data application areas are connected and automated vehicles, crowdsourcing, freight, ICM, planning, shared mobility, smart cities, traffic incident management, transit ITS, and work zones. And we're hoping that this will be available via the NOCO website this fall. And so we have been working with the AASHTO Data Committee to kind of find a home for this, and NOCO was generous enough to offer to host this for the project. So we've developed a shared mobility data resource guide. This is a curated guide to reference material to help agencies plan for, manage, and use shared mobility data. It categorizes and summarizes the content of 40 references so that the reader can identify quickly, which of the resources best address their needs and issues. As you go through, it summarizes the relevant literature, provides sample documents and agreements, discusses relevant standards and open source software, talks about the organizations that are active in this area, and provides examples of data sets and dashboards. Again, we reached out to industry, a lot of the organizations and agencies that are active in this area, got a lot of input, did a lot of research to find what resources were out there, and pulled this together and had it reviewed again by some of the people that were interviewed, and got some very positive feedback on the document itself. And this was just recently approved for publication by TRB. So this guidance document can be made available at this point. Data decision tree for big data and freight transportation planning operations. The target audience for this is freight transportation planners seeking guidance on which data sources best address their specific planning and operations use cases. And specifically, it highlights available big data sources and other complementary sources to address these use cases. It's built using a JavaScript library. And it basically, it's like a tree. So when you click on one node, it sort of opens up and you can kind of follow the specific, applications to the data sources for a particular use case. And once you click on that, it expands information on the data source. It shows metadata for that particular data source, as well as different use cases that are out there that have been done by agencies. And this was based on research and input from 7 state DOTs, the Eastern Transportation Coalition, and a private freight subject matter expert. The draft product has been approved by the panel, and we're hoping that the final tool should be available this fall. And this next slide gives you a little bit of an idea of the visual, starting with the freight data use cases, and how you can kind of click on these various nodes, and the tree expands until you get to a data set, and then you can get information on that data set. This is the metadata, but you can also click on the use cases and see how the data has been applied for specific use cases by agencies. Guidance and demonstration for improved conflation and geodata reference process. This product has been named Linker AT, and basically what it does is it cross-references disparate network data using a modified network conflation process. It was specifically designed to cross-reference Arnold network data with the TMC network data. And what it does is it updates the Arnold base network by adding links and nodes so that it better matches the TMC segmentation. It's an open source JavaScript program running in a standard Windows environment. It has all of the libraries and instructions built in, so there aren't any special libraries needed. It's a simple web-based browser user interface. It outputs updated GeoJSON files, including cross-references for associated TMC IDs. And it's easily modified by built-in routines to help states customize the operation for their specific inputs and specifications. And currently we're working with Colorado DOT to test it out. And we have run it for the Colorado network. And that's a map kind of the outputs of the process run, or the software run for the Colorado Arnold and TMC data. But Colorado is going to be testing it for more recent TMC, and Arnold data sets, and hopefully, working with the DOT to get some inputs to how we can improve the documentation of the guidance or the process itself. Guide for managing sensitive shared mobility data. This is helping to inform public agency managers on issues relating to protecting sensitive information that might be gathered as part of shared mobility and micro-mobility programs, such as scooter and bike sharing services and ride sharing and ride hailing services. And the sensitive data that's covered is really data that could be associated with identifying specific individuals or data that might be considered proprietary by the service providers. So the guide provides recommendations and guidance for how to protect the sensitive information through a step-by-step process that looks at determining the use cases where the data are needed, identifying what types of data are needed and what subset of the data might contain proprietary or PII. And then providing guiding principles and policies for managing the data and describing protection mechanisms to secure the data. And this product is, the draft has been submitted and is under review by the project panel. Using connected vehicle data and data fusion to supplement transportation systems management. So this product provides guidance to establishing uses of CV data for planning, operational, and safety analyses. And the purpose is to bridge the gap between CV and ITS systems and discuss opportunities to develop infrastructure while advancing the quality and resolution of the data. The guide discusses general CV system architecture, CV standards, a data fusion methodology, and then various vehicle and pedestrian use cases for transportation management with CV systems data. And we're just about to finish up the draft product, and hopefully we'll get that submitted to the panel very shortly. Another product is agency case studies on the use of smart work zone devices for work zone data feeds. So this product focuses on kind of highlighting current and future practices for integrating smart work zone data with agency work zone data, and particularly the work zone data exchange specification feeds that are being developed by many agencies. When we talk about smart work zone technology, the case studies will cover roadside devices such as smart arrow boards, connected cameras, and connected geolocated pins, as well as technologies such as dash cam videos and automated image resolution or recognition that helps to identify work zone locations. And we are working with a number of agencies to develop case studies for their current and kind of future practices, including Iowa, RTC, Southern Nevada, Kentucky, Massachusetts, Washington State, and also the Road Device Feed Project. And this project this product is currently under development, and we're hoping to have the draft complete by the end of August. Another product, fostering interoperability between freight data sources. So in CFRP Report 35, implementing the Freight Transportation Data Architecture Data Element Dictionary identified the need for an interoperable freight data exchange format to help address differences in data element definitions across data sets. And so the hope for this pilot product is to develop a preliminary interoperable freight data system architecture. And we're working with stakeholders to explore some of the strengths and weaknesses of a data interoperability structure, a specific one, as well as the opportunities and challenges in adopting it. And so this is currently under development, and the figure out to the right is just an attribute mapping of how we're looking at various attributes of the data, different data sources, and trying to map those across in developing this this architecture. State of the practice for ICM systems. This is at the very beginning stages of development. It is providing sort of an update on recent ICMs and really looking at agency use cases, recurring challenges, lessons learned, particularly when it comes to data needs and agencies' needs when you're integrating or working with different agencies that might have different objectives for the corridor, and how those are addressed and overcome. Data use for operational improvements, and recommendations for improving interagency coordination. Traffic incident management data guides. This product is also at the very early stages of development. The focus here, it's really 3 short guides that will focus on communicating information about sharing, integration, and management of data to support TIM performance measurement. So there'll be a TIM data sharing guide that, because you've got so many different groups in traffic incident management, DOTs and external partners like law enforcement and fire and rescue and towing. And there are challenges with sharing data across. And so this will focus on, some of the lessons learned and recommendations and benefits of doing that. And then the last bullet will kind of stem from those lessons learned in an outreach document that transportation agencies can share with their partners to help encourage data sharing and discussions about data sharing. And then there'll also be a short guide on data quality and use and some of the limitations of the current data sets and how to improve data, incident data. And then finally, use and value of crowdsourced data integration. Again, these will be a couple of short guides on the challenges, lessons learned, steps taken, and recommended actions for integrating and using crowdsourced data. And a lot of this will stem from the Federal Highway Everyday Counts 5 and 6 initiatives that have been going on over the last 4 years. There's a lot of states that Federal Highway has been working with to advance their maturity in using crowdsourced data, particularly for operations. And so these guides will be based a lot on the case studies of the uses and lessons learned and challenges from those EDC initiatives. Project timeline, I kind of tried to say as we went through where we were with the product development. We do have 1 product available for publication, several drafts under review by the panel, and hopefully will be available for publication this year. Hoping to have all the products drafts completed by the end of this year. And once the online resource website is approved, we will be adding those, making that website available and adding those products for public consumption. And again, project ends approximately May of next year. And I just wanted to share some of the team's contact information. Again, a really great team of people helping to leading the development of these products. So if you're want to know more about the products, I'm certainly happy to address any questions, but Dan at CETA at Jacobs is leading the freight tools. Mike McGurran has led the shared mobility guides. At Granzo of Jacobs, the conflation tool, and Brian Burkhard of Jacobs, the ICM product, and Vaishali Shah, the crowdsourcing products. So thank you very much, and I'm happy to address any questions.
Thank you so much, Callie. This is great. When we start looking at all the potential that big data has, we forget how much goes into the data integration and processing. And this is a very important product for practitioners, for sure, to know not only where to find this information, but also how they can use these data sources. So this is very good. I thought the conflation tool is very interesting, especially for a state that has so many TMC segmentation. It's very helpful for them to be able to do that data integration. Thank you again to all the presenters. I don't see any questions on the Q&A chat pod or on the chat. So if you want to raise your hand and ask your question directly to the presenter, please feel free and I'll allow you to talk. In the meantime, I just have one quick question for Nicola and Sean. So it may be more applicable to the Cranberry use case, but probably for both of them. When you developed that model for incident detection, I saw that you had integration data fusion for several data types. Did you consider crash data on that analysis? Did you look at the effects of this model for incident detection on crashes? And I was particularly thinking of secondary crashes that we know they're high occurrence, you know, on state routes and highways.
Absolutely, that's a great question. We particularly making sure when we did a case study that all the incidents, general incidents, not just the crash. Of course, crash is a very important part of the incidents data, but also down trees, weather conditions, snowing, all included in the both the state kind of fed data as well as waste, which is social media data. It's all included. Well, as to the modeling part, so it's a little bit tricky because you can use different techniques depending on the sophisticated level of the models that you use. You know, some models can adapt to these anomaly detections much faster than others, but at the price of more computing and more data for training. So I think it's a compromise. So, but in general, if you apply the proper models, the machine or the statistical model, you know, regardless of what type of model you use, it should be able to pick up the impact of these incidents if the data kind of the model adapt to the data right. Does that answer your question?
Yes, thank you. Thank you so much. And I don't see any other questions. We did have a request for the link to the report, and the report has not been published yet. If they want to get more information, can you please, Nicola and Sean, give them a contact information where they could ask you questions about that?
Sure. I think we'll probably put James' contact information. I can put that in the chat as well.
Okay. And I don't see any other hands. All right, if we don't have any other questions or comments, thank you everyone for attending today's webinar, and especially to our panelists. Great presentations today and a very good discussion. I particularly enjoyed learning about those examples that you shared with us. As I mentioned in the beginning, the recording for this webinar will be available at the NOCO website. And there are other resources as well available for you if you want to find case studies or other technical resources related to data and decision making for operations. Be sure to check the NOCO website. And Nicola already posted the contact information for their study. And on behalf of the National Operations Center of Excellence and all our presenters, thank you so much for joining us. And have a great rest of your day. Thank you so much.
Thank you.
Thank you.
Thanks. Bye.
Bye.